All right, hello and welcome back to week 2, everyone. So I guess the first place to start is that the government has said that we won't be able to meet until at the earliest, I think the middle of February. So I guess that means we'll probably be doing something like this for, I guess, this week and two or three more. Um, yeah, so I guess that's the first thing to say. The second one is that next week we will have a quiz. So along with the videos, I will go and put a list of a couple of questions up into the discovery page, or I guess in an announcement. Um, and I will pick one of those questions. I will make it a quiz question. The format will be um, that I will send out an announcement with the question, and I will hold everyone to their honor that they will take no more than 15 minutes, close all the resources, just pencil, paper, or if you want to do it on an iPad or something, just something to write on either physically or digitally, and just your cognitive abilities, no notes or anything. Um, right, potential things with projects. Um, I am hoping that the government is at some point going to let us meet together, but as time goes on, I get increasingly doubtful that that is going to happen. Um, so the way that I'm thinking about how this project will work for now, I suppose this is subject to change based on how we're allowed to proceed. But what I figure is please be thinking about a data set that you want to work with. Um, if you could come up with ideas of what you would like to do, ideally by the end of the month, that would be good, because then as we start introducing more techniques with probability and such, that gives you an eye towards thinking about things that you can do. If you have a good idea of um, something that you would like to do, as we go and we introduce more topics, you can hear something and think that, well, that actually might be very practical to implement to what I want to do. So the way I'm imagining this is that um, you will write up some techniques in R, and you'll write a short report. Short meaning um, that what you are writing is as long as it needs to be and no longer. So if you think it needs to be 20 pages, then that is okay. If you think you've said everything you need to say in one page, that is also okay. I'm very flexible on these kind of requirements. So that's what I'm thinking about. I would have liked to have it set up so that we could meet in person and everyone could present what they've done, because I think that's fun and it gives everybody an opportunity, um, to speak in front of others, and that's never a bad skill to have. Um, if we're not going to be able to meet in person, I really don't see a point in doing an actual presentation, but I don't know. I could be open to doing something like that. Um, yeah, okay, so on to the videos. So in this one, I'm going to go and do, I think it's chapter 2, and I'm going to talk about sample variation, and then I'm also going to do another video that's going to combine some of the R things to know from this section, and then I'm also going to do stuff from chapter 3. So I'm going to more or less knock those two out today. And then, kind of as I'd mentioned in the last video, what I'm thinking is that if we're going to have this time frame, um, or if we're going to not be able to meet in person, I might constrict the time frame a little bit and then use the last couple of classes to go and introduce some extra stuff. You wouldn't need to know it for tests or anything, but I think it'd be really useful things to know. And it would allow you to get a lot more out of especially R and allow you to see some different things. So I think that could be kind of interesting, and we'll see how things go effectively. Okay, so the first thing that we'd want to ask is, what is a sample? And I guess the simplest way you could think about it is when we could all still go to Costco and roam around. Costco would have all their free sample tables out, so you would I don't know, they would have a beverage or maybe some pizza or something like that, and it would be sitting there, and so it'd be kind of a sliver of a pizza, you could get a sliver of a pizza. So the simple way of thinking about a sample is it's a slice of something much bigger, and you want to get a feel for what's going on with the big thing based on the little thing. So if you try a sample at Costco of something and you like it, you might be inclined to buy it. So you want to take insights from the small thing and ideally get good insights into the bigger thing. In the case of Costco, buying some food item or otherwise, here we want to go and ideally be able to make some kind of inference about uh, some characteristic of our bigger population. So the population that we're considering could be pretty much anything in different contexts. You could be looking at, um, well, population for a vote. You could be looking at products coming off of a machine. So you want to test for machine quality. You go and you look at a collection of the products that have been produced to see if the machine is doing what it ought to be doing. You could take a sample of water quality from some body of water to go and see if there's too much pollution in the body of water or something like that. So just a handful of places where we could see samples showing up. Okay, so one example that I've done is I've taken all of the games from the 2018-2019 NHL season for Alexander Ovechkin, and what I want to do is take a sample of those games. To start, I'm taking samples of 10 games and trying to figure out the average number of shots that Ovechkin had in a game for that season. The correct answer for this is just over 4 and 1/6 shot per game, so 4.17. So I would go and take all of the games, randomly choose 10, see how many shots he took in those games, take the average. Right. So in the first one, the first sample, we have 4 shots, 7 shots, 5 shots, 5 shots, 4 shots, 4 shots, 7 shots, 11 shots, 4 shots, 5 shots, and that comes out to an average of 5.6 shots in a game. The second sample I took, different collection of games, and there I only get an average of 4 shots a game. In the third one, I get an average of 5 shots a game, and then in the fourth sample that I took, I got an average of 3 shots per game. So if you didn't know what the correct answer is here, it might be kind of hard to tell because we're looking at something that's ranging between 3 and 5.6. Um, that's not great. There's a lot of wiggle room in between there, especially because we're dealing with something like shots by a player in a hockey game that's probably not going to be that big. So when you have something where the number you're looking at is not that big and comparatively um, the range of values you're getting from your sample is comparatively large, that says you'd like to take more um, more sample points. Right, so I did that. So then what I did was I took samples of size 20. And here we see that the range we get is still kind of big. The first sample that I took comes out with an average of just under 5 shots a game. The second one is just under 4 shots a game. The third one is 3.3 shots a game. And the fourth one is 4.25 shots a game. But one thing that we do see is the range on these samples is smaller. Right, so in this one we had as many as 5.6. Here we had as low as 3. Here we've got as many as just under 5 and as low as 3.3. And we know that um, we know that the correct answer is a bit over 4.1, a bit under 4.2. And as we take more and more samples, we get that um, bound around where we get the bound around the samples that we're getting is going to get closer and closer to that center. And eventually, if you took a sample of size 81, which is the total number of games that Ovechkin played that year, you would get exactly 4.17. But the whole point of taking a sample is that you don't want to look at the entire population to go and figure out, in this case, the average number of shots in a game. The whole point of the sample is to be able to simplify down the amount of information you need to be able to make accurate conclusions. And then for interest, I haven't included it here because the list would get very long. But for interest, I went and increased the sample size to 50, so more than 50% of all the games played, something like 60% or so. And once I did that, the sample sizes or the sample values that I was getting were somewhere between about 3.9 and 4.4. So getting very, very close to that correct value of 4.1. Okay, so one way that we could measure variations present in data is to just look at how often each number is showing up and draw conclusions from that. So what we see here from the first sample that I took with just choosing 10 games is the number 4 shows up 4 times. So there were 4 games with 4 shots in this sample, 3 games with 5 shots, 2 games with 7, and 1 game with 11. So one would tell. So from this, you could maybe say the data is not varying that much. Most of the 7 of the 10 values that we're getting here are either a 4 or a 5, which tells you that it's not going to vary that much. And then same kind of idea for the second sample. So where this was one of the ones where I took 20 shots in the game. The average here was just under 4. And here we see is even though there are 20 shots taken in total, 5 of them were 2 shots a game, and 6 of the games had 3 shots. So again, this tells you there's not necessarily that much variation. If you saw that the numbers were kind of more spread out between 1 and 11, or maybe we had something else that had a broader range to it. So maybe we were looking at points scored in a game by a basketball player, and that was ranging between maybe 10 and 50. We could get things kind of more spread out. There'd be more variation in that. Okay, so then we also want to talk about when sampling goes wrong. So some of these are you could be trying to take a sample of a population and you could, as far as you're aware, do everything right, but things still don't work very well. So one problem that you might run into is you getting non-representative sample. Okay, so what might an example of that be? So suppose that you were going around a university and you wanted to get a view on the prevalence of alcohol at the university. And and you went to the local temperance club and asked them for their thoughts on the prevalence of alcohol at the university. They would probably say that alcohol is highly prevalent at the university. But if you went to a fraternity, um, they might say it's no big deal. So depending upon, so if you did something like that, you pick a bad sample and it doesn't represent the population at all, you're probably not going to get very accurate outcomes. It could also be that you are dealing with data that's got a lot of errors in it. So suppose that with with the hockey games, the number of shots wasn't accurately recorded. So maybe some of these ones where there were 3 shots, there were actually 4, or where there was 8 shots, there were actually 6, or something like that. If the data starts getting very inaccurate, you simply won't be able to draw accurate conclusions from it. The old phrase with that is garbage in, garbage out. If you get bad numbers coming in, the conclusions you're going to make based on the bad inputs aren't going to be very good. One of the problems is knowing when you have bad data and possibly being able to fix it. And depending upon the context, those could be hard problems. Maybe you know ahead of time that you're dealing with data with errors in it, and there are ways of fixing it. If that's the case, then then sometimes it's worthwhile to go and try and correct them. Other times, if the number of errors that you have is comparatively small, but you could easily identify them, maybe you want to throw them out. But depending upon the context of whatever you're working in, depending upon the errors, how prevalent they are, how hard it is to deal with them, that'll change how you want to go and deal with your errors. Another kind of problem that you could run into is what's referred to as self-selection bias. So something here is where you run into a bias based upon the makeup of the people you're sampling. So one example that I could think of that I've noticed is that when dealing with math classes that take place early in the morning, if you're wanting to take something like a calculus course at 8 or 9 in the morning, that means you're probably very dedicated to the course. because most people who have no real interest in calculus are going to want to wake up and do it at 8 or 9 in the morning. So what I found is that um, you'll get a lot of good students showing up to these math classes at 8 or 9 in the morning. And if you want to evaluate, so say you have teachers who are teaching different sections, some are early in the morning, some are later in the afternoon, and you see that the one teacher who is teaching calculus class at 8 in the morning, his students have very good test averages. But you have another teacher who's teaching at 2 in the afternoon, uh, same course, they just teach, they maybe teach differently or whatever, and the person teaching at 2 in the afternoon, his class has lower test scores. The inclination might be to say, well, the teacher who's teaching at 8 in the morning is a better teacher than the one who's teaching at 2 in the afternoon. But it might be that it actually has nothing to do with their teaching ability whatsoever. You're dealing with the dedication or um, ability of the students themselves is coming into play. You could run into issues with sample size. So you might take a sample that is too small. We kind of saw that a moment ago with the difference between taking samples with 10 shots versus 20 shots, or 10 games versus 20 games. If you just took a sample of the 81 games, just taking 10 games, um, you might not wind up with a very accurate um, perception of how many shots per game Ovechkin was taking. So you could get something that's kind of a shot and a half more, a shot and a half less, or something thereabouts. But as you take a little bit bigger of a sample, so maybe 20 games isn't enough, maybe you need to take 30 games, but you take a bigger sample, it gives you a more accurate estimate of the thing you're trying to study, which in this case was shots per game. Influence. So influence would be something where the way the sample is conducted biases the result. So maybe it's something where you have someone who is asking questions to respondents, but the questions are kind of loaded in a way that suggests um, an answer. So maybe a question is posed and there is a moral implication that suggests that the respondent um, is a good person if they answer in one way versus another. And you could do something like that and you could influence the respondent to answer in the way that would present them as being the better person. Causality. So causality would be an, an example of causality is where you have two quantities that you're trying to tie together, and it appears from the results that you have a relation between the two, but there's actually a um, third, or maybe there's some other factor that you don't see. So, for example, there are estimates that about 20% of all Americans who are over 7 feet tall will play in the NBA at some point in their lifetime. Now, someone who doesn't know anything about basketball might hear that, and that might lead them to the conclusion that being over 7 feet tall grants some special ability to play basketball. And in a sense, that's true, in another, not necessarily. The factor that's linking these two is that, first of all, there are not that many people over 7 feet tall, and number two, um, there is a there is almost a necessity factor of being freakishly tall in basketball, and basketball, out of all the other sports, has a natural attraction to have people who are 7 feet tall or more playing in it. You could have a a study or a sample or something like that where the group that is behind running the sample or the study or the survey or whatever has an interest in the results. So suppose, for example, that you had a study put out by Marlboro that says that smoking tobacco is perfectly healthy and does not cause any health complications to you whatsoever. Well, Marlboro would very much like that to be true. Um, so sometimes when seeing the results of a study or a survey, it's not a bad idea to keep in mind who is behind the results. That doesn't necessarily mean they're wrong, but it's not a bad thing to um, keep in mind people's motivations effectively. Um, okay, and the final example that I have here of ways that sampling could be done wrong is what's called confounding. So confounding could be that you have a whole bunch of variables at play, and it's very hard to tease out the impact of all of them. So suppose you have a hockey line, and you want to try and identify which player on the line is responsible for driving offensive production. It might be fairly hard to actually tease out which of the players is responsible for the production, or maybe which one or ones is hindering offensive production from this group, and any conclusion you might have might just be kind of a mashup of the influence of everybody at the same time, and it's very hard to identify where the influence is coming from. Okay, and then one last example of where sampling could go wrong is from this famous quote from Mark Twain: "There are lies, there are damned lies, and there are statistics." And this is where it's not so much the sampling that is going wrong, it's that there is some willful antics to go and make the conclusions be to go and manipulate the data, we'll say. Or maybe not manipulate it, but to um, prevent, present truthful information in untruthful ways, we'll say. Okay, so one example that I have from this, and I've kind of anonymized what this example actually is, just for convenience. So there was a study that was done that was looking to see the effectiveness of an intervention. So the results from the intervention are in black, the results from the non-intervention group are in the orange-yellow line. And what we can see from this plot is that the group that had the intervention did worse. This is not one of those cases where um, you want to be bigger. This is one of the cases where bigger is badder. So the scoring on this one was like golf. You want to be smaller. So in this case, the non-intervention group was the one that had the better outcomes, clearly at every point over this entire interval. The intervention started on July the 3rd. So it started right here. We can see that the black is clearly above the yellow-orange, and where they finished, the black was still above the yellow-orange. So worse at the beginning, worse at the end, and worse at every point in between. What happened was that the way the study was done is that they waited 6 days to pick the starting point for what they would consider to be the beginning of the intervention. So instead of starting when the intervention began on July 3rd, they started somewhat arbitrarily 6 days later. And what we see is that in between when the intervention began and July the 9th, there was this massive spike, which was not good, in the intervention group, and there was a comparatively slight increase in the non-intervention group. So then the way that the study was conducted was they looked at the starting point and they looked at the ending point. And what we can see from this is that if we take July the 9th to be the starting point for our intervention, the result at the end of the time interval, I think, was August 23rd. The intervention group saw their statistic drop slightly. I think it went down about 6%, whereas for the non-intervention group from July the 9th to August 23rd, their numbers doubled. So the way the study was presented was that the intervention dropped the statistic for the intervention group by 6%, but for the non-intervention group, their statistic doubled. So what that says is the intervention was a success. Well, the problem is that if we look at this chart, which shows what the intervention and non-intervention numbers were, the intervention did not work whatsoever. And especially if we went and started when the intervention actually began and compared that to the end date, what we'd see is actually the intervention group also went up substantially. It might not have doubled, but it still went up quite a bit. Okay, so that goes and gives us kind of an overview of sampling and some of the things that can go wrong with it. Some of the things that can go wrong with sampling are maybe things that the sampler has no control over, other things they do. Um, so also, this gives you some tools um, to think about whenever you're seeing statistics presented, to just kind of maybe watch out for some things like this. You see something like this with studies. Um, Checking out methodologies is always a good thing. Okay, so I'm going to end this video here, and then I'm going to have another one where I go and I do a handful of things in R, and then I'll put those two up in Discovery.